So, welcome to this lecture. Before this, let me sum up what we did so far. We have seen that how that AC circuits can be analyzed exactly in the same manner as of that of DC circuit. Once you represent this AC sources and the circuit components into phasor domain, or you say frequency domain. Once we represent them in frequency domain, you can solve the circuits in a similar fashion as you do for DC circuits, except for the fact that the circuit is in phasor form, and you get the results also in phasor form, which you can later very straightforwardly you can change it into the time domain. So this was one of the examples which we took to analyze using mesh analysis. Before that, we also did the same circuit using nodal analysis, and we saw that our results, voltages and current, come out in phasor form, and that phasor form like this it comes, and that can be this phasor forms can then be easily put into time domain form. It is quite straightforward. Okay, once we know that what was the existing frequency in the circuit, that gives you, and we know the phase difference or phase from this part, and that is straightforward. We can put as voltages or current, whatever the case may be. So now we'll talk about various theorems which we did in DC circuits also. We'll do it for AC circuit in a similar manner. As far as if you know how to solve mesh and nodes analysis, you can solve all the Thevenin equivalent and Norton equivalent. Just for the sake of completion, we will take Thevenin theorem for AC circuits, and here we'll see what are slight differences are there. Not differences, rather due to representational things. We now have voltages coming in phasor form, and the Thevenin equivalent resistance which was there in DC will come out as impedance, Thevenin equal impedance. So let us see what we have to do for a circuit. If we want to have Thevenin equivalent of a circuit, all you have to do is to represent all the sources and impedances in phasor form, assuming that they are given to you in a time domain, voltages etc. and in time domain. So you have to convert into a phasor form. Most often phasor form is quite popular, and you normally get circuit already in phasor form itself. So whatever the case may be, you have to do the analysis in phasor form. Then you remove that part of the circuit across which Thevenin equivalent is to be found. So if this is circuit A, and you have to find the Thevenin equivalent here, and from here there is circuit B. So you have to remove the circuit so that you get A like this, so that you can find the equivalent, Thevenin equivalent, across terminals A and B. So that is what is meant here, that you have to remove the load part or the other part of the circuit for which you are finding the equivalence. Okay, so with this A, you can calculate equivalent, Thevenin equivalent voltage, and then also calculate Thevenin equivalent impedance. And you know how to calculate Thevenin equivalent voltage. Basically, Thevenin equivalent voltage is the voltage across A and B, terminals A and B, and that will be now coming in form of phasor here. As far as AC circuits are considered, rest all the methods are exactly same as DC analysis. So you have to take the circuit and find the voltage across A and B, and similarly you have to put off all the sources, kill all the sources. So killing all the sources or putting off all the sources means you have to put the voltage sources as by a short circuit. Voltage sources are equivalent to a short circuit, that means making voltage sources equal to 0, and current sources equal to 0 means it is open circuit. So that is how you represent the circuit A for finding ZTH. And in that condition, if only independent sources are there, then you have to basically, if only independent sources are there, then you can easily remove all the sources or zero out all the sources, and then you have a impedance circuit, purely impedance circuit, and you can calculate equivalent impedance seen across A and B, that is ZTH, and that would also come out to be complex because now we are talking about AC circuit. And if you have a dependent source, then it has to be kept intact, and the way you have done in case of DC circuit, it is not removed, and you have to keep that in the circuit and then find ZTH in a similar way by putting a voltage across A and B and then calculating the ZTH. So that is how you actually proceed if there are dependent sources. Once you calculate ETH and ZTH in phasor form, you can also find the equivalent time dependent circuit, okay, or time dependent, not current here, other here I mean circuit. So a time dependent circuit, that means source ETH can be put as in a sin omega t form and ZTH as a complex form. So that is how you can do in a equivalent circuit. Let us take a example here. Simple small example is there. So here it is meant that this is circuit B part, that is only a resistance R and that is load, and basically the question says that we need to find equivalent across A and B. And if you see here, we are not given the circuit is not given in time domain, rather it is already in phasor domain. So in actual practice, we normally have all the circuits now put in phasor domain because it is quite popular. We do mean that what E10 raised to power voltage V angle 0 means we know that it is a sinusoidal source, and this is XL 8 ohm and this is XC, that is XC, and this is for 2 ohms XL. Okay, I think J is missing here. I think J is missing here. J is missing here, so we have to put appropriate J's over here. So I think this is J 8 ohms and this is minus J 2 ohms. So that is what for which you wish to have Thevenin equivalent, and that is what you have as Z1 and Z2. And if you want to find voltage across A and B first, so you can find voltage across A and B, and how you find the voltage across A and B will you can just see that it will be basically Z1 upon Z1 plus Z2, and this is a phasor form, and E, that is 10 angle 0, this will be actually E Thevenin, and I think you can calculate, and it comes out to be somewhere around 3.3 volts. Let us try to see if it is so. So it is 8 and 2, so they are coming this way. This would be something like 10 Z1, that is XC, so J2 ohm with a negative sign divided by J8 minus J2 ohm, Z1 plus Z2 into 10 angle 0, so this comes out to be minus J2 ohm upon J6 10 angle 0. We are calculating ETH, okay, voltage across here A and B, and by this we get this as 1 by 3 minus J, or J get cancelled here, so minus 1 by 3 10 angle 0, so it is 3.33 angle 0. So that is what is calculated here as ETH, and since it is minus negative, here minus was there, therefore it is either you put it minus 3.33, or if you put in a magnitude form, normally you have to put a magnitude form, which is always possible, always done, always positive magnitude, so it has to be included in angle, so it gets minus 180 degrees. And then this is Thevenin equivalent voltage, and then you can also find ZTH using this circuit. So here if you see this, the voltage source is put to 0 by short circuiting it, and now you can find out the value of ZTH, which comes out to be this. It is basically, if you see, it is a parallel combination of Z1 and Z2. Okay, so you can easily calculate the parallel combination, and it comes out to be this. So this is how a equivalent circuit is calculated, and this is across A and B, and then you can put the value of R if you want, or this is basically the equivalent circuit up to this point. So this completes example for a Thevenin theorem. We have, if you know how to analyze, you can do it for any kind of circuit. This is just for illustration purpose. Now the second part, once you have done Thevenin theorem, let's see how to do Norton theorem. Norton theorem also, you have the same process. If you go here, you have the same process, except for the fact you have to calculate I Norton here, and ZTH is same. And what is I Norton? Basically, I Norton is calculated by short circuiting this terminal and finding the value IN. This is what the Norton current is, and for ZTH it is exactly the same. So we'll not go into again saying how to do it, because that is same. We will just take up example here and try to solve this. So here again I have taken the circuit already in a phasor domain. Resistance is there and XL is there, so possibly here J is missing, and this is XC, so it should be minus J5 ohms, and that is all. And this is the load resistance. So this is circuit B, and this part is circuit A, and these are the terminals across which you wish to have the Norton equivalent. So for getting the Norton equivalent, what we have to do is we have to short circuit these terminals A and B. Short circuit here, you have to remove this and short circuit this part and find the value of IN. That gives you the Norton current. And finding IN here is exactly the same way we did in the last example. Okay, that is, here if you see, it will be E upon Z1, because this gets short circuited, and this is what you have. So E, if you see, is 20 volts angle 0, 20 angle 0, and Z1 is this impedance, which is basically 3 ohm resistance and J4 ohm reactance, and that is what IN is. And I think if you calculate, you have to convert this into polar form and calculate it, and you get IN as this. So I think 3 squared, it is 25, no, it is correct, E by Z1. This comes out to be 9 plus 16, 25. Okay, so it comes out to be 25 root, so it is 5. So it will be 4, and angle will be there, some angle would be there, which is tan inverse 4 by 3. So whatever that angle is, it seems it to be 53.13, and that is what you have as IN. And then you can find Zn by looking through in this circuit in a similar way as you do for ZTH, except for the fact that in equivalent circuit it comes in a parallel or across the current source, and that you can see that it is again a parallel combination of Z1 and Z2, and that is ZTH, and this is what you have Zn. So this is now equivalent circuit for norton equivalent circuit for the given circuit, and this is additionally put here to find the current if you want to. So I'll stop here for now. Thank you.